Good afternoon, London. I hope you're having a great summit. My name is Mariano Vecchioli. I'm originally from Argentina, but really, who needs sunny weather, delicious steak, and amazing wine all year round, right? So I moved to London, and I became a TAM for AWS. As a technical account manager, I focus on continued operational architecture and cost efficiency for workloads that enterprise support customers move to AWS. Time and time again, customers have told us about three fundamental pillars on which they build both enterprise and next generation applications. And those are security, scalability, and availability. As with any other product that Amazon develops, elastic load balancing is developed backwards from our customers' requirements. And it all starts with security. Imagine that you have a service. It could be a web server, it could be an API, whatever you want. Typically, what you'll do is you'll have an elastic load balancer sitting in front of it. And you'll terminate your SSL and TLS traffic there. Now, everything that we'll cover in this section is security, independent of the actual load balancing capabilities of ELB. The first thing that we do on an ELB is terminate our secure connections. If you create an elastic load balancer, you can choose to terminate your SSL and TLS traffic there. You just need to upload a certificate and a key. And you can do this yourself, or you can ask us to do this for you through AWS Certificate Manager. So how do you ensure that the SSL and TLS implementation is kept up to date? Well, that's easy. We manage that for you. So over the last few years, we've seen a number of vulnerabilities come out. We've seen Poodle, the SSL v3 fallback issue. We've seen Logjam, which is an attack on Diffie-Hellman exchanges. And we've seen Heartbleed. And I have a special place in my heart for Heartbleed. I've seen developers and sysads run around for days trying to patch everything under the sun. So how fast did we resolve these issues for ELB customers? Same day. The only thing that you need to do when a new security issue comes out is log on to the console and update your security policies. But it's not just reactive. We also do a bit of proactive work. We removed RC4 in advance of it becoming an unreliable protocol. How do we do this? Well, we like to dive deep when it comes to SSL and TLS. And we came to a crossroads where we needed and we decided to have our own implementation of them. We decided not to trade off security and performance, so we developed S2N. It's open source. You can go browse the code on GitHub. Please wait until we finish here. And it is subject to intense review and audit. We don't want to stop at our internal development teams. And that is why we're full active members of the SSL TLS community. And we make sure that we're at the forefront of collaboration whenever any security issues come out. We have AWS Certificate Manager as well to make things even easier. So managing your own certificates and your own keys can be a bit of a chore. You've got to generate it, you've got to copy them, you've got to email them to someone, you've got to open a ticket to someone to upload them to your actual ELBs. With AWS Certificate Manager, you can log on to the console and just create the certificates. You can then associate them to an ELB. It takes about 5 minutes, and it's free. You don't want to leave your terminal? There's an API for that too. We try to make everything as simple as possible. Thank you. We try to make everything as simple as possible. And how do we manage this behind the scenes? So how do we make it so easy to update these security policies? Well, you can just log on to the console, and with a few clicks, you're on your way with the default settings. But we do a couple of things in the background. So we have lists of preference for Cipher Suites. And some of those are perfect forward secrecy. So we subject all of the traffic that comes through the ELB to an extra step. And that's a Diffie-Hellman algorithm to make sure that we protect past information for future compromises. In other words, if an attacker gains access to one of your secret keys today, they will not be able to decrypt any of the traffic that they recorded yesterday. That's a pretty cool feature. We also do a little bit of work on the standards. We prefer AES over 3DES and RC4, which guys, you shouldn't have enabled. Please disable it if you do. And we do a little bit of work with authentication algorithms as well to help make traffic a little bit more tamper-proof. So we prefer GCM over CBC and HMAC. And we don't just put these policies out. It's not just like we build a list and push it out to you guys. We actually test all of these criteria on billions of real-world connections with real-world clients. We want to make sure that you're secure and available. But of course, there's always the old legacy client out there. There's the old legacy system or embedded device that is using a Cipher suite that has been deemed to be insecure. So how do we manage this? How can we help customers migrate away from those insecure Cipher suites? Well, access logs. Now, you might not think about them as a security feature at first, but access logs contain a world of information that you can parse and that you can leverage to make your infrastructure more secure, even reacting to events in an automated fashion. So you can pipe all of your ELB logs to an S3 bucket, and with the correct cross-account policies and permissions, you can ensure that if anyone were to actually gain access to your environment, they wouldn't be able to remove the most important thing in tracing the attack back to them, which is the logs. And that doesn't mean that you have to go out and build your own data lake and your own parsing tools. We've got customers here at the summit today, such as Splunk, SumLogic, and Lockly, who can provide you with tools from the marketplace to help you do higher level analytics and deep dives. One of the most interesting things is that we log the actual Cipher suite that was used to negotiate the request. And this is important. So say that you want to upgrade all of your protocols, say that you want to upgrade your application, but you need to find out who's actually using what Cipher suite where. You don't want to upgrade and suddenly break something for someone somewhere. So you enable logs, you enable the access logs for a couple of days, you parse them with your own tools or one of our partners' tools, and you can figure out who's using what where and reach out to them before doing the upgrade. Using ELB as a known defensive layer is one example of compartmentalization. What we've seen in terms of security patterns is that our customers are launching ELBs into public subnets using VPC. They then apply security groups from the VPC and IAM role accounts and permissions to ensure that that becomes a known layer through which public internet traffic is piped. It becomes effectively the only way to open up a port to the internet. Customers can then have a degree of confidence that outside access is protected and correctly filtered, and they can become a lot more agile in their private subnets. We also support CloudTrail logging. It's fully supported within the ELB API. And creating and launching ELBs into these public subnets is a known and traced activity. So whenever someone does it in your environment, you can go back to who did it, when, and go ask why. In addition to this, we have the ELB access logs, and you can enable VPC flow logging. So these are network-level logs that will give you a vast amount of information on what TCP connections or what TCP traffic is coming in and going out of your ELBs. All of these that we've discussed so far help keep things really tight and really constrained. And it all feeds into the security threat model, helping you protect against common security concerns. All very cool features that help you ensure that your environment is secured and up to date. But the real job of the ELB, as we all know, is, of course, scaling. And this is where it gets really interesting, guys. This is where you get jiggy with it. ELB at its root is a scalability product, right? So it takes small or huge loads and balances them across the estate of EC2 instances on the back end. So how do we understand how we need to load balance things? Well, there's a law called Little's Law, and it's one of the fundamental laws of applying load to distributed systems. And it's really, really simple. All it says is that your system's ability to process load is directly proportional to the amount of requests coming in versus the time that it takes to process each one of them. So in short, your system is going to become more latent the more load you put on it, and it's going to become faster the quicker that you can process every one of those requests and the least time that each one of those requests sits there waiting. Now, what causes latency. One of the most common causes of latency, and one that people don't usually consider, is garbage collection. If you're using a programming language that implements garbage collection, then your system is not going to be serving requests while the garbage collection is active. And the garbage collection will kick in once the heap size is full. How big your heap size is will depend on how we've configured your JVM. Too little RAM, too big a heap, and your garbage collection will have to kick in very often, denying the ability to process requests. And another common reason that we see is caching. A lot of applications have caching layers, or caching at different layers. So if a request happens to come in for a bit of data that is sitting hot on the cache, then that's great. Absolutely amazing. We've got the data right there. We pull it out, return it to the client, and that's it. But what happens if your data is cold? What happens if we have to go to disk? Or worse, what happens if we have to go to a remote database? All of that adds to the latency that your system has when serving requests from the outside world. So generally, if you have an instance serving traffic, and this is for a single instance, your time to serve each request will look a little bit like a log normal distribution. So you'll have really good initial response times, but your average will be a little bit slow. And your 99th percentile will be really slow, taking up to a second or more to return the request. So how do we improve this? Well, first we have to look at what this looks like in a queue format, right? So if we put this in a queue sort of like diagram, we can see that there's a multitude of requests, all of different sizes and characteristics. And they're all sort of queuing up, one after the other one, waiting for the instance to serve them. And this is, of course, quite inefficient. So some of the requests can be a few kilobytes in size and be in hot cache, which means that we can serve them out really fast. And some of them might be quite large. If you're requesting a monthly report, we have to go to a database, we have to do a number of queries, a number of joins, and then return the result. And that can take a long time. So again, when you have that sort of processing criteria, your average will be really, really bad. And what can we do to improve this? So what can we do to improve this situation? Well, we can throw more capacity at the problem, right? Instead of processing things linearly, we can start processing things in parallel. And that will certainly help. So that will make your averages a lot faster. It will make the initial time of response incredibly fast, but you will still have a long tail. And the reason for this is that even though you've added capacity, you're still processing things in a linear queue. So there's a sequence of packets coming in, small and big, that need to be processed. If we separate the requests and send them all to different instances, we do get a benefit. But there's more things that we can do to actually improve this situation. So we can use weighted round robin to distribute the load across all of the instances. And this will improve things. So the orange line there is a single server, and the green line is the weighted round robin across multiple servers. It helps pull in the tail a bit, so your worst case scenario is not going to be that bad. But we'd like to do things differently. Even though we like to parallelize the workload, we don't think that sequentially processing those requests is the best way to do it. So how do we do it? We play Snake. So essentially, in the previous queue, what you had was a single file for each agent or each server that would process the request. What we try to do is we try to queue up the requests and route them to the next available server. And what we do is we do a least connections weight distribution. So the idea is that we'll identify the load that each of the components of the system is under, and we'll route the next request to the component with the least load. This will smoothen the peaks. So you bring down the average, you bring in the tail, and this is what the benefit of ELB is, right? So as long as there is capacity available, as long as you have a server that can serve that request that is coming in, that's where the ELB will route the request to. There is a caveat with this. You have to be very, very careful not to black hole the traffic. And what does black holing mean? So if you have a number of servers, you have a number of components, each one of them will have different response times. And it might be the case that one of them has a very long response time because it's getting all of the really long bit of the tail end requests. But it might be that others are responding really fast. The faster that you respond, the sooner that you get a new request. Now, what happens if the response is not actually an expected response, but a 500 error, an exception, or whatever else is not what we're asking for? Then that server will start getting all of the requests. And that will cause a bit of a problem. A nice, easy hack, if you have an application that is processing requests, is to just put in an exception handler, which has a delay in responding. So even if the response is going to be an error, you put in a little bit of a sleep, let's say 100 milliseconds or something like that, and that will attenuate and avoid black holing the traffic. So how do we scale ELBs, right? Because this is all really good. How you scale ELBs, you scale on the back end, but how do ELBs themselves scale? Because they are the single point of entry for all of the traffic. So all of the traffic that eventually reaches your instances first has to go through the ELB. So we see customers serve anything from 2 to 1 million requests per second using ELBs. And we use 2 types of scaling on the ELB platform. One is preemptive, which means we scale up the ELB as long as you're putting more instances at the back end. We assume that you have a very, very good reason to put those instances there. We assume that you are expecting traffic to hit your ELB. So we'll scale up, and we are very, very aggressive at scaling up. We will scale up a whole lot, and we will remain scaled up, even for days, even if we don't see traffic. And we also scale reactively, which means that we look at your traffic patterns, and we try to scale ahead of those hitting your ELB and your infrastructure. We also use CloudWatch, or you can also use CloudWatch to scale up. And the idea is that every single metric in CloudWatch can be used to scale up. Now, some of them might not be too useful or immediately obvious, and you don't need to build your own metrics. Like you just take the CloudWatch metrics that we offer and plug and play into your auto-scaling. We provide 13 CloudWatch metrics. All of them can be used for scaling. And you can also configure alarms to let you know when your solution is scaling up and by how much it is scaling up. We also offer a complete view on the end-to-end life of the requests going through your solution so that you can understand whether processing is getting slower, whether the life of that request is getting longer. And this is very useful in understanding whether you can target any optimization opportunities at the application layer or at the solution layer. And we also offer 2 metrics, SurgeQueue and Spillovers. So what SurgeQueue does is it queues up requests that your backend is not yet ready to process. And the idea is that we create a queue that holds up to 1,024 requests. And once your backend becomes available to process these requests, we slowly release them. There's a good reason for not going above 1,024, and is the stampede effect. So we found it that by turning requests away after 1,024 queued up requests, we give the application time to recover. If you have a high count of spillovers, then you should start looking at the backend and thinking about scaling up, choosing a different instance type, or even looking at the application for optimization opportunities. And we also have access logs. Other than for SSL and TLS purposes, access logs provide a vast amount of information for you to understand what's going on with your application. It's a bit more verbose than your Apache log, but we found that this information helps customers do a really deep dive into what's going on with requests, applications, and the backend. And in addition to regional availability, we also support scaling through Route 53. So you can create a DNS domain name, and you can route traffic based on GeoIP traffic, GeoIP traffic, least latency, or whatever other metric you can use. So this is very useful for customers that have applications where latency is critical. So advertising, exchange, or bidding. And this ties very well into availability. And to speak about availability, I would like to welcome onto the stage Ben Doyle, Senior Infrastructure Engineer for Ensighten. Please welcome Ben.
I'm good. How's it going, folks? My name is Ben Doyle. I too hail from a tropical climate like Mariano, the exotic island of Ireland. I work for a company called Ensighten. We're a web analytics company that have two main tracks of products that will hopefully give you some kind of context about how important ELBs are for us. The first one is a data collection product. So our customers will drop a pixel on their website so they can start to track users' journeys through their website, see if they bought something, what kind of ads they came in on, and what's generally working for them and what's not. The other kind is like a content management system that's referred to as tag management. So we need to be really on point with this, because if our tag management service stops working, we're in danger of hindering the availability of our clients' websites. Their websites might not load properly or might not load at all. So we need to be as close to the end users as possible. So we're across lots and lots of different regions with a DNS tier in front of our ELBs that geo-route and also do health checks as well, DNS health checks. So the nature of these two products give us two very large problems to solve. The first one is we have compounded traffic coming in. So we have quite big clients, so United Airlines, Samsung to name two. Anytime you visit one of those websites, we also get a request to our infrastructure as well. The second, arguably more difficult problem to solve is we need to explain on a daily basis to our families what in actual fact we do in our company. But many people here, I'm sure, have that problem that they have to solve in their own way. So AWS have a pretty big tagline about ELBs, and it is that ELBs provide seamless and graceful replacement of instances with no downtime. Now, I hope there's no one here who is living in a world pre-load balancers, but before load balancers, and even some of you still might have to do this, there's functionality mainly powered by health checks gives you a functional way of solving problems as well as solving operational problems as well. So traditionally, you might have a server up with your version of the application running. You want to do an application upgrade. You need to get your engineers up at 2 a.m. in the morning. They do not like that. Take down the service, schedule downtime. You might lose some requests. Clients might get angry. Hope that you complete the maintenance within the maintenance window. Bring it back up, and hope all goes well. With an ELB, if you have an instance running your application behind an ELB, what you can do is you can bring up another instance with the new version of your application running, add it in behind the ELB, see if the health checks pass, and then you can remove the other instance that's running your older version of the application from the ELB. Don't worry about requests that are still going to the old instance. When you remove an instance, or when it fails health checks with an ELB, client traffic that's in flight will still go to that old instance. So you can watch the connections drain and then see the new instance or the new application version take the hits. So we use these to our advantage in Ensighten. We have an Ansible run that can be easily applied to any kind of orchestration tool or config management tool, whereby when we want to do a minor or patch upgrade to our applications, the Ansible run basically goes, OK, I'm going to get a list of the instances behind this ELB. I'm going to take the first one on my list. I'm going to force the health check to fail so that connections still go in, so all the connections drain off. Then Ansible kicks in, copies down the new version of the application, edits the config files, bounce the service, whatever have you, and then start to make the health check when it deems as healthy again. What Ansible then does is it waits to see if the ELB accepts the instance back into service. If all goes well and the health checks do pass, then Ansible goes on to the next instance, repeats the exact same process. If the health checks don't pass, Ansible screams, "Human, what have you done?" And the engineers need to log onto the box. It stops there. It doesn't go on to the next instance and deploys a bad version of the application. We've got an instance ready to go with an example of what hasn't worked and the problems that we need to solve. So hopefully we can fix that, run the Ansible run again, and all will go OK. So these are two kind of functional problems you can solve with health checks. The other one is operational, which is probably quite obvious, but I'll quickly run through it here. We have 3 EC2 instances behind an ELB. All running the same application. The top instance there, that's meant to be the CPU bar on the far right. Something's gone wrong. The disks are full, CPU's pinned. There's a bug with the application. Either with CloudWatch alarms, the ELB sending health checks. Those application health checks start to fail. Traffic starts going to that instance. It starts going to the other 2 instances. Through alarming, whether it be CloudWatch or your own internal services, an engineer is notified, logs onto that box, fixes the issue. The ELB sees that instance starts passing health checks again, gets added back into your backend fleet. So health checks are really key when it comes to configuring how much value you get out of the availability aspect of an ELB. So ELBs offer two kinds of health checks. One is a simple TCP health check, whereby it just needs a TCP response. So it's the equivalent to running netcat or telnet to a certain port and getting the open reply. So that might be fine, but a web server that's serving 503 errors will respond with a TCP check, but your application might still be throwing errors. So this is where the HTTP health check is quite useful. HTTP health check, you point it to an endpoint in your application, a URL on a certain port, and the ELB will need to get a 200 OK response back from that health check. Otherwise, it doesn't count as healthy. If it gets 503, 404, a timeout, the ELB will consider that unhealthy, and after the threshold that you configure, it'll remove that instance from service. So this kind of gives you the ability to configure a kind of depth to your health checks. So at Ensighten, one of our products has a web tier that's dependent on a database tier. So if that database tier in that region goes down, the web tier also goes down in that region. So what we have is a very light health check that hits the instance, and that the instance then goes off, does a read from the database, and returns 200 if it's OK. If it can't get to the database, returns a 503 or does something strange, the health checks fail. And then you go, oh, well, hang on, all your instances are going to start failing then. But that's OK, because at our top tier, we've got the DNS health checks running. That will fail us over to another region. When the ELB has no healthy instances behind it, we fail over to another region. That's hopefully working. So another feature of ELBs that you can configure to kind of figure out the health of your application or how it interacts with your request is the idle timeout feature. So an idle timeout for an ELB, what happens is when a request comes into an ELB and it forwards that request onto the instances, a counter starts. And basically, it waits until the request comes back. And if it waits a number of seconds, that's to your timeout, it's taking too long, it's going to close the connection and close the connection to the client. So this is quite useful if you want to fail hard and fast with your applications. You might have built into your own client somewhere that, OK, well, if I get a bad response, I'm going to back off a bit and then connect back again later. So this is where this is quite useful. So idle timeouts, by default, they're 60 seconds. You can have it as low as 1 and as high as 3,600. Pretty useful giving the monthly report example that was given earlier on. So you don't want your clients waiting too long for that monthly report to come back. But you need to have a think again, like you would with your health checks. Don't shoot yourself in the foot with it. So if you configure the diagram here, if the monthly report takes on average 20 seconds to complete, and you set your idle timeout to 15 seconds, then really that request is never going to successfully complete. The ELB goes, man, sorry, you're taking too long. I need to shut that connection down to the client. So you shouldn't just configure this on your ELBs, but you should also configure it throughout down the rest of your stack, and the timeout should get lower. So in Nginx or Apache or your Rails stack, whatever, you should determine how long a timeout for other back-end dependencies should take to respond. So in this example here, at the very bottom of the stack, we have our EC2 instances make requests to S3 RDS in simple workflow. And they think, OK, well, 9 seconds is an OK time for these to respond. So the instance is 9 seconds. ELBs is going to be a little more generous to the instance in case it needs to do some number crunching. After it receives that data, it's 15 seconds. So you need to be careful with that. And you need to have a think and apply the correct value to your stack. Another thing to keep in mind as well is the idle timeout connection setting on your clients as well. So by default, a lot of browsers have the idle timeout, I think it's between 60 and 300 seconds. So if you set the idle timeout to above what your client is, the client's going to go, nah, close that request, and you're going to have issues. So one of the key takeaways from using ELBs that you should bring away today is that you should always have your ELBs associated across multiple availability zones with your instances. What this enables you to do is basically survive in the event that an AWS availability zone goes down. So you give an ELB 2 subnets. In this case, we have one ELB on this diagram, but it's associated to 2 subnets, one in US West 1A and the other in 1B, along with EC2 instances behind that. So if 1A were to go down, we're still OK. The ELB is still there for you in US West 1B, as well as your instance there, and your application can continue on. There's no kind of black magic that goes around in the background. here. There's no kind of complex control plane call for the ELB. It's just simply DNS health checks. So Route 53 is constantly going, health checking the ELB nodes and your AZs. And once it realizes that they're failing health checks, it's going to stop returning that IP address. So you don't need to log in. You don't need to wait for someone in AWS to flick a switch or anything like that, because as on this screen here, rather than reacting, we have a system on the left that's reacting when a failure occurs. But on the right, we have something like the ELB system where it's constantly checking if everything's OK. So therefore, the time to react is much more, a lot faster. So again, key takeaway, 2 or more availability zones. Subnets are mapped to a single availability zone, so give it 2. Make sure they're in different regions, or availability zones, rather, and associate those to your ELBs. So having said that, it does bring in a few challenges. When you've 2 availability zones, what you can start to see happen is you have traffic imbalances. So on this screen here, we have a request count from an ELB that's split across 3 subnets across 3 availability zones. We can see that the green availability zone has a lot more requests than the other ones. And more often than not, the cause of this is a DNS caching issue, because while you have the various load balancing algorithms Mariano went into before with the HTTP and TCP listeners, on the top level, it's just DNS round robin to figure out which ELB node to give the request to. So some clients, looking at you, Java, don't obey DNS TTLs. The program starts up, goes, oh yeah, that IP address will do. I'm going to hang on to that until I restart. Great idea. So what can start to happen is, again, back to this diagram, the bottom ELB node, in this case, has its IP address cached by a bunch of clients that aren't obeying DNS. So all the requests start to go to that instance in US West 1B. How you can get around this is by turning on cross-zone load balancing, which is a pretty handy feature. In the previous slide, cross-zone load balancing was turned off. So the ELB nodes that are associated with your subnet in US 1B are only going to load balance to your instances that are in US West 1B. With cross-zone load balancing, all the ELB nodes register all your backend instances to themselves. So what you can see start to happen is that ELB node at the bottom is load balancing to the instance in availability zone A. And then you get much nicer traffic matchup there. So again, it's a feature that you get for free. One small little disclaimer is that you're going to see a small jump in network latency when you turn it on, because rather than the request going into the same availability zone, that ELB node needs to make a request across to another availability zone. In a lot of cases, it's negligible, and for us, it's quite negligible as well. So for us, really, kind of to conclude my part, is that ELBs, I don't, as an engineer in Ensighten, they're one of the biggest workhorses of our infrastructure, and I really don't have to worry about them a lot. They're incredibly reliable. I get my metrics from them that I can tie into other systems, and they work great with a lot of the configuration management tools, whether it be infrastructure as code like CloudFormation or Terraform, as well as like Ansible and whatever else have you. So they work quite well for us, and I'm sure they can work quite well for a lot of you guys as well. So I'll pass over back to Mariano for the recap then.
Can I have the clicker? Yeah. Thank you, Ben. Today, we've covered the fundamental pillars of elastic load balancing, which is security with a fully managed SSL TLS stack, AWS certificate manager so that you don't have to copy and toss your security credentials around, easy association with your ELBs within your AWS account, not needing to go outside of it, and compartmentalization, which sounds hard to say, but it's really useful for driving security in your account. With all of these, you can make sure that you have a fully secured and up-to-date solution. And it removes the need for you to have to concentrate on running around patching boxes and worrying about something that is anything other than your work and developing your application. We've also looked at scalability, how ELB scales up, how it takes care of distributing load across your instances, and how we make sure that the ELB is capable of processing all of the traffic coming into your environment. We've looked at CloudWatch metrics, which you can use to scale up your instances automatically. We've looked at access logs, which will give you both a security insight as well as an ability to scale up if you need it to. And we've looked at global scalability, scaling across regions, using Route 53 to make sure that you make the best use of your environment, your infrastructure around the world. And we've heard from Ben about minimal downtime, seamless replacement of instances when an ELB fails. We've heard about the health checks that you can leverage to ensure that your solution remains highly available. And we've looked at cross-zone load balancing to remove traffic imbalances and overall optimize the efficiency of the traffic going through one end to the other of your solution. Please remember to rate this session if you have the time on awssummit.london. I hope you have enjoyed the session. I hope that we've managed to give you a good insight into ELBs. And please join me in thanking Doyle for joining us today on stage. Please have a nice day and enjoy the rest of the summit.